before I get into a new section, I will do a little MATLAB demonstration about the previous section. It actually will help set the stage for a new one. So this will be a demonstration involving convergence. Right, so I'm going to show you an example of convergence involving an approximate second derivative. That's one of the things that I showed last time. So the approximation to the second derivative of a function at some point x naught is given by this expression f of x naught plus h, or minus h, minus 2 x naught plus f of x naught plus h, all over h squared. So what I'm going to do is show you how this kind of approximation behaves for an example for which we know what the exact result is supposed to be. So for this example, I'm going to set f of x equal to sine x. My x naught will be pi over 4. And then I'm going to use for value of h at the outset 0.1. So now I'm going to set these values. So x naught is pi over 4, h is 0.1. And then I'm going to define what's called a function handle. So f, to define a function handle, I showed this once in the tutorial, but we're showing again. Use an at sign, and then an x in parentheses indicating f is going to be a function of x. And in this case, I just want it to be sine x. So that way, I can just do, I can do an expression like this, f of x naught minus h, f of x naught, and it'll work as intended. Okay. Now, so I'm going to compute an approximation to the second derivative.
So what's with the at sign?
The at sign tells MATLAB that you're defining a function. So now I can pretty much do exactly this, and I need the asterisk multiplication. So f of x minus h minus 2 times f of x naught plus f of x naught plus h squared. Oh, it's a good idea to do format long if you have it already. So here's my approximation. Now this doesn't really mean anything because we need to know, we need an exact value comparative. And I'm sure that you all being math majors or math graduate students can tell me second derivative of sine x.
I was format short.
Oh.
Negative sine.
Yeah, negative sine. Okay. Do you have format long now? Well, go ahead and do that. Okay. So the exact value will be minus sine of x naught. And, well, at least it's in the ballpark. First couple of decimal places agree. So to get the error, I'm going to do, this is a concept from the previous section, relative error. So that's going to be, use absolute value, because we only care about the magnitude of the error. Absolute value would be approximation minus the exact over absolute value of the exact. And let's see what we get. So our error is, okay, so reasonably small number, 8 times 10 to the minus 4. That's what this scientific notation format means. Okay. Now, okay, then, so let's see what happens if I use a smaller value of h, because ideally, this approximation should converge to the exact value of the second derivative as h goes to 0. Now, before I had h being 0.1, so now I'm going to do 0.01. And then I use the up arrow to compute the approximation again with the new value of h. So same value for approximation as before, but it's going to be using different h. And if we just eyeball exact versus the new approximation, you can see we're closer. So now I'm going to go back to this command to compute the error again.
Go back to error.
Yeah, so repeating this statement. And then take a look at the errors that we got. So the first time, with h equal 0.1, it was on the order of 10 to the minus 4. And then the second time, with h reduced by a factor of 10, the error is on the order of 10 to the minus 6. So decreasing h by a factor of 10 decreased the error by a factor of 100, or 10 squared. So this shows, numerically, if it's proved by MATLAB, that the approximation has the error that is big O of h squared. So the error is proportional to h squared. In other words, another way of describing it in words is second order accurate. So if we were to continue this, let h get even smaller, so like 0.001, then I would expect the approximation of error on the order of 10 to the minus 8. And it does. So thinking, okay, why not just keep going? All right, let's try 10 to the minus 5.
Went back to the h's.
Yeah, so a new value of h, and you have to compute the approximation again, and then you compute the error again. So now I'm decreasing h by a factor of 100. What? Yes? Notice I changed the value of h.
Change the value of h?
Yeah. 0.001.
Well, I didn't see the value get changed.
Well, it was right there on the screen. When you repeat the approximation, okay, then now look at the error. 10 minus 8. Okay, and now I'm going to try changing h again. 10 to the minus 5. Now before, h was 10 to the minus 3. I decreased h by a factor of 100. So the error ought to decrease by a factor of 100 squared, 10,000. So I should get error that's on the order of 10 to the minus 12 the next time. So I go ahead and compute the approximation again. And let's see what happens with the error. And the error increased. So that's not good. That wasn't what was supposed to happen. But here's why it happened. The error that we get in its computation is not just stemming from the error in this formula that approximates the second derivative. So computations in general have errors coming from multiple sources. So for this approximation of a second derivative, the error in this formula, the discretization error, that's one source of error. But now we're seeing another And based on, and that's, this discretization error really does go to 0 if h goes to 0. The problem is that we have another source of error that's rearing its ugly head. And it's actually round off error, which is the subject of today's section. So if I were to go even further, like if I let the h be 10 to the minus 7, and then I recompute the approximation, and then recompute the error, it just keeps getting worse and worse. So this is the worst approximation of all.
Worst approximation of all.
Of all the ones I've done today. So, and that's what would happen, that the if I were to let h get smaller and smaller, the error would just keep growing. So what I'm going to do to demonstrate this more visually is I'm going to create a vector of h values and approximations to go with them. So to do that, I'm going to use a for loop. Okay. So I'm first going to create vectors of approximations and so you're going to create a vector of h values. And to do that, I'll have 10 dot exponent, and then I'm going to have exponents ranging from -1 all the way to -15. So I need this vector using the colon operator. I start counting at -1, and I keep counting backwards all the way to -15. Okay. Actually, I'm going to transpose the vector, just because I like column vectors. So
You're transposing the.
yeah, this quote here causes a transpose. Because colon operator produces a row vector, but I want a column vector. So here's 10 to the -1, 10 to the -2, and so on, all the way down to 10 to the -15. Nice visual there, I guess. So now I'm going to use each of these, okay, I get a QT approximation using each of these h values. But instead of doing one at a time, I'm going to use a for loop. That'll handle it for me. So I'm going to do approximations for each h value. So I go for I equals 1 to 15. And then I'm going to set h equal to my vector is called hs. I use the s for plural h's.
Approximation.
So I take h to be an element of this vector, and then I can scroll back through my commands to get to compute the approximation with that h. And then, okay, yeah, it's the same command as before. You can use your up arrow to get to it. And then I'm going to compute the error again. But I'm going to store that in a vector also. So error I, comma 1. So this is going to create a column vector on the fly. And in the I position is going to put the error for this approximation. I'm going to add a semicolon here. I don't want printing everything. Okay. And then I can end the for loop. And now I have all my errors. And let's take a look at it. We see the numbers get really, really large. 10 to the 14th. So at first they're very small. That's when the approximation was accurate. But then it kept getting worse and worse.
Excuse me.
Yes.
I'm not getting a recognized value of.
You called it error instead. So type error instead of the whole word. Go.
Error.
Yeah. Yes. Yeah. Okay. Now you have it. So it just yours just has a different name. Now, seeing this vector, we can't really tell what's going on because all these values appear to be 0, but they're really not. So what I'm going to do is I'm going to plot the error versus the h values on a logarithmic scale. That's good for visualizing order of magnitude. So I do log. So
Logarithmic scale.
yeah, so log is similar to plot, except it plots on a logarithmic scale on both the x and y axis. Okay. Okay.
And then enter.
Yeah.
Wait. Oh.
Your name is different. Your variable names. Okay, yeah. So what's happening here is here we have larger h values over here. The error is going to 0, or h squared. But right around here, there's a turning point, and the error starts to increase. So what happens is, over here, the round-off error from these computations is negligible. So what we're seeing here is discretization error. But as h gets smaller, round-off error becomes larger and larger. That becomes the dominant one. So it was possible, which is not really practical to do, to separate discretization error from round-off error, and we could focus on discretization error. This trend would continue as h went to 0. But what you're seeing is always the sum of all the errors that are in play. So that's why in this next section we're going to focus on this source of error, round-off error, and how it can lead to some unpleasant surprises in your computation, such as this one. And as I mentioned on the very first day of the semester, people have literally died over it. All right, so I'm going to turn off this diary, and I'll be posting this later. Okay. Let's save the fig file. We'll post that later.
Diary off. You're turning the diary off?
Yeah. Okay. So any questions about what happened in this demonstration of convergence? How it doesn't always happen? Okay. So, what I need to discuss first is, how are numbers represented in most computer systems? And certainly ones that are used by MATLAB. So the simplest way to describe it is it's like scientific notation, except it's in binary, so base 2. So the way the number is represented as the number x has plus or minus, and then we have this number m that's called, apparently this term isn't used anymore, but at least for relics like me, we call it the mantissa. I think it's now called like the significand or something like that. And then that's multiplied by some base, beta, raised to an exponent, capital E. So you can think of m, the mantissa, as containing the significant digits of a number. And then beta to the E accounts for the magnitude of the number. Now, the base, beta, we're all accustomed to beta being equal to 10, decimal. But computers work with beta equal to 2, binary. So here's an example with the number x being equal to 117. So if I want to represent this number in base 10, so beta equal to 10, then I'm thinking it as plus 1.17 times 10 squared. So the exponent capital E would be 2. The mantissa consists of 1.17, which we naturally interpret, without even thinking about it, as 1 times 10 to the 0 plus 1 times 10 to the minus 1 plus 7 times 10 to the minus 2. So these digits are all associated with non-positive powers of the base. So that's important to keep in mind for doing the same in binary. The mechanism is the same, is that because we're not accustomed to binary, we have to think through it. So same number, 117, representing in binary, beta is equal to 2. So the magnitude is accounted for by 2 to the 6, because 2 to the 6, or 64, is the largest power of 2 that is less than the number. So 117 falls between 2 to the 6 and 2 to the 7. So that leads to the exponent being equal to 6. So I guess it's the greatest lower bound of the integer exponents. Okay, so then the mantissa is the original number divided by 2 to the 6. Now, how do we represent that? Using these binary digits that correspond to non-positive powers of 2. So this 1 to the left of the, I guess now I call it binary point, is just 1. And then this digit, the 1 right after the point, corresponds to 1/2. The next one corresponds to 1/4. And then here we have a 0. So the next position is 1 over 2 to the 4th. And then this one corresponds to 1 over 2 to the 6th. So all of these together give me the number 117 over 64. So this is the floating point representation of x in binary. So any questions about how numbers are represented in binary versus decimal? Here's a formula for the exponent. You take the absolute value of your number, and you take a logarithm in whatever base you're working with, 10 or 2 or whatever, and then this notation, the weird bars with the little feet on them, that's floor, a floor function. So you take the logarithm in that base and you round down to the nearest integer. So that's how you can get the exponent of any number in whatever base. So then you take beta raised to that exponent, so your base raised to that exponent, and you divide the absolute value of your number by that, and that's what gives you a mantissa. So here we see how to get the value of both. Now, but as for how do you get the digits in a particular base, that can be a tedious process if you're dealing with a base that you're not accustomed to. Okay. So a first digit of your mantissa is just the integer part of your mantissa. And then after that, you subtract it off, and you keep multiplying by the base, move up the next digit. So I'm going to show you an example of what I mean by this, because I know this is totally not clear at all. From the text. Okay, so I have an example here. The number in question is e, the base of a natural logarithm. So roughly 2.7183. And I want to represent this as in binary to a certain number of digits. So first I need the exponent. So I take the logarithm of e, but to base 2 rather than the natural log. And that gives me 1.4427. I round that down to an integer, and I get 1. So the exponent is 1. So the mantissa is going to be e divided by 2, 2 to the first power. So this number right here, that's the mantissa that I need to represent. But here, the mantissa is written in decimal. I want to represent it in binary. Now, this digit to the left of the decimal point is called D naught. That's equal to 1, so I just go ahead and take that. Okay, and then I subtract it off. Now I have this number that I want to represent in binary. So what I do is I take that number from subtracting it off, multiply by 2, and I get a number that is less than 1. The digit to the left of the decimal point is 0, so my next binary digit is 0. I have nothing to subtract off, because that is the digit of 0. So now I multiply by 2 again, and now I get something that is greater than 1. So my next digit in my binary expansion, D2, that's 1. Because I got a non-zero digit, I subtract it off. Then I multiply what's left by 2, it's still less than 1, so I get a 0 digit. And then I multiply by 2 again, I get something greater than 1. And so you see how the process continues. And how I can keep multiplying by 2 and subtracting off whenever I get a non-zero leading digit. And the end result is, this is my number if I go up to 20 digits in binary. And the way I get the value of this is, for each non-zero digit I have, I multiply it by the negative power of 2, or non-positive power of 2, corresponding to its position. So here I have this leading 1, this gives me 1. Then I have nothing, then I have second digit is 1. That's the binary point. So then I multiply that by 1 over 2 squared, 0. And the next one by 2, 1 over 2 to 4, and so on. And adding all of these up gives me this. So my floating point representation of E is, here's my mantissa times base raised to the exponent. The exponent is just 1. And this is the number that I get. So this number here, 2.7813, that's an approximation of E. I get pretty close to representing it. But there's still some error here, 10 to the minus 8, which corresponds to roughly 2 to the minus 24. Okay. So any questions about how we get the floating point representation of a number in binary? Now we go like, you took the language, just get all this, we get out of here. Yeah.
Why does it represent?
What?
Why do they choose to represent this way?
What? Why binary?
Yes.
Because computers run on electricity. Signals 0 versus 1.
Okay.
Yes, like 0 for off and 1 for on. Although supposedly at one point in Russia they had a computer that used base 3. I don't know how they did that, like physically, like that on, off, and kind of on. I haven't looked it up, but yeah, it's a thing, or it was a thing. I guess they decided not to stick with it.
question?
Oh, here's the, so it's, so the general form of the mantissa is given here, where we have digits that have to be between 0 and the base minus 1. Yeah, that's this condition right here. By convention, the leading digit should be non-zero. The total number of digits we can have, p, that's called the precision of a floating point number system. That's something we're going to be looking at. Also, the exponent, capital E, is limited to a particular range. So E is must be greater or equal to some value capital L, less or equal to some value capital U. So you're limited to a range of magnitudes. You also have limited precision. So that's the key property of floating point number systems, is that there's only so many numbers that you can represent. Yeah, and this is that same representation here in whatever base you have. So these four numbers, beta, p, the precision, and L and U, the lower number bounds in the exponent, those are the defining characteristics of a floating point number system. They indicate what numbers can be represented in terms of a limited precision and limited magnitude. So first, I'm going to focus on the magnitude. There are two problems that can happen with representing numbers: underflow and overflow. So if you have an exponent that is below the lower bound capital L, you're talking about a number that is too small to be represented in the floating point system. Now that's not really a big problem, because you can just declare the number to be 0 and continue your computation. Overflow is when numbers get too large. So the exponent becomes greater than the upper bound capital U. So the number is considered infinity. And if I were to demonstrate with this in MATLAB, I'll be posting 2 diaries today.
Two diaries?
Yes, sorry.
Two diaries. Two diaries.
So for example, if I want to enter this number into prompt, 10 raised to the 1,000th power. MATLAB doesn't like that. It's too large a number, so it calls it infinity.
Infinity and beyond. It calls it to infinity and beyond.
I guess so. So if I do this expression, 1 over 0, because we know that's to be undefined, but and MATLAB takes a step further, it also calls that infinity. And if I do minus 1 over 0, so we have minus infinity also.
Why is it? Yeah, it's allowing us to divide by 0?
Well, yeah, but you can't do anything meaningful with it. So
No, why does it make that justification?
Yeah, well, I guess because the limit as x goes to 0, 1 over x is 0 is.
Okay, hold on, y'all are both on.
The limit as x goes to 0 of 1 over x being positive infinity.
Because you're adding the constant zeros that get to 1 for any constant.
But what about 0 over 0? I mean, we've all been trying to think of 1 over 0 and 0 over 0 as bad. But there are different kinds of bad, aren't they? do we call 0 over 0? What kind of expression is that? Indeterminate form. Because it could be anything. I mean, 1 over 0, it's too easy to think, okay, that's something that's going off to infinity. But 0 over 0, you have no idea what it is. So, if I enter that into MATLAB, NaN, not a number.
Not a number.
Yeah. When you get this, you know you really messed up. And you should rethink your life. But, kidding. Well, I guess you want to get philosophical about it, yes. But this is more so. Okay. Now, the floating point system used on most computers is the IEEE double precision floating point system. So what are the parameters in this system? The precision, P is equal to 53.
Triple E.
And then the lower bound on exponents is 1020, minus 1022. And then the upper bound on exponents is positive 1023. So these are the smallest and largest exponents that you're allowed to have. And then I'll fill in p equals 53 also as a variable. Okay. Now, okay, then the base, of course, is 2 because it's binary. So these are the 4 parameters that this floating point system uses. Now, before I do anything with that, I'm going to return to the notes for a bit.
B equals 2, semicolon.
Alright, so what we need is what we have is called the overflow and underflow levels. So the smallest and largest numbers you can have. So the overflow level is defined to be the base raised to the largest exponent plus 1, and then times 1 minus the base raised to minus the precision. Now, this is a totally meaningless expression to any of you, I imagine. But to explain what this expression means, if I were to do this in decimal, base 10, that would be like having 9.9999 to however many digits p that you're allowed to have. So if this was a decimal system, then okay, sorry, that's the largest mantissa. So this expression right here, parentheses, beta minus beta to the minus p minus 1, if beta was 10, it would be this. And then that's multiplied by the base raised to the largest possible exponent. Okay. But written this way, what we see is the largest possible number is therefore equal to a number that's slightly less than, because this is a number that's slightly less than 1, the base raised to the largest exponent plus 1. So in a decimal system, your overflow level would be this kind of number with p digits times 10 to whatever the largest exponent is. But in IEEE, double precision, we have these parameters to work with. So what I'm going to do is I'm going to put this expression with these parameters into MATLAB. So for the overflow level, called OFL. So if I do same expression, b raised to the u plus 1 power times 1 minus the base raised to the minus p power.
Overflow that.
So let's see what we get here. It says infinite, which means I messed up. The reason why I should have gotten an actual number here, but the reason why I didn't is because I should not have done this. That number is too large. Now, yes, this is multiplied by a number that is slightly less than 1 to make it a little bit smaller. So the overall value of this, if I could compute it, would be okay. But because in the evaluation of this expression, it computed this first, that's too large, the whole thing was judged infinite. So instead, you need to use the upper form of this expression, where I'm raising b raised to the u power, and I take one of these factors of b, or beta, and I distribute it through here. So I'm multiplying by b minus b raised to the minus p plus 1. So now the number b to the u is okay, and then it computes this value that's slightly less than b, multiplies that. So in this case, I get my value. So that number is, so it's roughly 1.8 times 10 to the 308. So in decimal, this is the largest exponent I can have. So that's why the number I typed in the very beginning, 10 to the 1,000, that was too large.
I got my result in
What?
format short form.
Oh, okay. Oh, then you can always change the format along. That has a special variable called real max. So that's meant to refer to the largest number allowed in a double precision floating point system. And if I enter a variable here, sure enough, I get the exact same thing. There's also a variable predefined by MATLAB to be the smallest number. And let's see what that is. Real min, or smallest positive number. All right, so pretty small magnitude, 2.2 times 10 to the minus 308. Although I have to tell you that that's actually not the smallest number that can be represented. Because this number, it is 10 to the b to the l, so which is the same as 2 raised to the minus 1022. Okay, that's what it's giving me. Now you might think, oh well, isn't that the smallest possible number? Well, in terms of the exponents, yes, but you can get smaller numbers. Okay, so as far as so I have this expression for the overflow level that I just covered earlier. Underflow level is base raised to the smallest exponent, but it has to be multiplied by the smallest possible mantissa. And the value of that depends on whether numbers are normalized or not. So the value given by real min is just assuming a smallest mantissa of 1. But we can actually, under certain circumstances, we can have smaller mantissas than that. So this gets into the whole issue of normalizing numbers. So if the leading digit of a mantissa, so the number to the left of a point, is non-zero, then that's the convention we normally use, then we say it's normalized. So here's an example, 3.14. So normalized, we write it this way. We have this number, but we can also write the same number this way, and that is not normalized because we have a 0 to the left of the decimal point. So there's compelling reasons to do either normalized or not normalized. One good reason to normalize numbers is that each number has a unique representation. In the special case of binary, we get an extra digit of precision. The reason why is, in binary, the only digits possible are 0 and 1. So if you require that the leading digit be non-zero, it has to be 1. So you don't store it. There's no need to, you know what it is. Whereas in decimal, if you require the leading digit is non-zero, it could be 1 through 9. So you still have to store it. Now, there's a disadvantage though. If you normalize numbers, the smallest mantissa you're allowed to have is 1. So you lose the chance to represent smaller numbers. So, so there are actually 2 possible underflow levels. So if you do normalize, it's base raised to the smallest exponent. So that's what real min gives. If you don't normalize, then you multiply that by the smallest possible mantissa, which is at 0.0000, however many digits you can have, with a 1 in the last position. So, so what IEEE does is called gradual underflow. So numbers are generally normalized, but if the exponent is equal to the smallest allowed value, capital L, then they switch to denormalized numbers. And one nice thing about not normalizing for small numbers is if you're if what you've stored for your floating point number is all 0, that actually corresponds to the value 0. So that's one problem with if you always normalize, you can't represent 0. So that would be a bit of an oversight. But now we can. In fact, we have 2 zeros. You can have 0 with a plus and 0 with a minus. So we have plus and minus 0. So here's how we can get a smaller number than this so-called real min. I can do 2 to the minus 1074, and I get a non-zero value. But if I go one step further, 2 to the minus 1075, it declares it to be 0. It's too small. So the idea here is that 2 to the minus 1074 is equal to your base 2 raised to the smallest exponent times 2 raised to the minus 52. That's the least significant digit in the mantissa because the precision p is equal to 53. So that gives you 2 to the 0, 2 to the minus 1, etc. all the way down to 2 to the minus 52, 53 digits total. So think of your mantissa as being 0.0000 and then 1 in the last position, and you put those 2 together, and you get the smallest number that you can possibly have when you're not normalizing.
Mantissa.
Okay. I just want to see how far I need to get. Okay. All right. So
I was still typing.
I do need to keep going. This is all going to be in the diary anyway. Okay, so what I've been talking about so far mostly concerns the exponents in magnitude. But what about the mantissa? We only have limited precision. So to represent a number that cannot be represented exactly because we don't have enough storage for it, we have to carry out rounding. So there are different ways of rounding. One is chopping. So that refers to always rounding down. So if you have a expansion of your actual number in your base, then you just cut off the expansion after you get p digits in total, and you just leave it at that. But you can imagine that's not always the most accurate choice. So that'd be like taking 0.899 and then rounding it to be 0.89, but it's really much closer to 0.9. So the better choice would be rounding. Now, the way we were taught to round, although I was taught to round in Massachusetts and most of you were around Mississippi. Now, one of those differences, not to mention a generational difference, who knows what they're teaching now. Okay, because how are we taught to break a tie? Like if we have, say, a number of 4.5, which is equidistant from 4 and 5. So what do? Or how were you taught originally, like in elementary school?
We're taught that around one that fits 5 or more.
Yeah, so in that case, you break the tie by just rounding up in that case. Now, what computers do instead is called round to even. So it will round either up or down, depending on which one of those will cause the final digit in the expansion to be even. So, as an example, if you have 89.5, you round up so that the last digit 0 will be even. Whereas 88.5, you're normally taught to round to 89. We actually round it down to 88. The reason why is to eliminate bias in rounding. So ties can be at a pretty much equal chance of being rounded up or rounded down. I should make a note of that here. Oh, wait, I already said it reduces bias. Okay. Why did I say that? Well, I did. Okay. Now, rounding leads to the concept of what's called machine precision, also known as unit round off. So, when you represent a number that cannot be represented exactly, like pi, for instance, there's going to be some error. So, this number of a bold U, referred to either as machine precision or unit round off, is the largest relative error that you could incur in representing a real number. Now, if x is your actual number you want to represent, then FL of x is a number that you get from representing it the best you can in your floating point system. So the relative error, the approximation minus the exact or the exact, the largest value of that is your unit round off. So what is unit round off? It depends on how you round. So it's your base to the 1 minus precision if you are chopping. So you're off by a whole digit in your expansion. It's cut in half if rounding is used. So that's a compelling reason to use rounding instead of chopping, even if chopping is easier to implement. So in double precision, it's equal to 2 to the minus 53, which is on the order of 10 to the minus 16. So that's one notion of unit round off. Another definition that is actually not entirely equivalent to the previous one, but is often used. The smallest positive number that you can add to 1 and actually get something that's considered greater than 1 in the floating point system. So in IEEE, it's 2 to the minus 52. So it's slightly different than this notion of unit round off. Now, if I, whoops. Zoomed out for a second. All right. If I flip, stop it. So go back to MATLAB. So if I take 1 plus 2 to the minus 52, notice it gives me just 1.00000. So there's something there. So it's not, so this is a number that's slightly greater than 1. In fact, if I take this number and subtract 1 from it, then I do get something. In fact, it's at 2 to the minus 53. Oh wait, no, this is 2 to the minus 52. So what I added to it. On the other hand, if I do 1 plus 2 to the minus 53, it just says it's 1. In other words, the 2 to the minus 53 got ignored. On the other hand, I've played around a bit. I've been able to add somewhat smaller numbers onto it, and I don't remember it correctly, but I didn't try this out. 2 to the minus 53 plus 2 to the minus 105. I add that first, and then add it to 1. Yeah. Now, this value is
Add all this to 1.
yeah. But you have to put in parentheses, so it's computed first. Now, this value is actually the same as this value because of rounding. But at least I can show that I could add something smaller but not on 1 and still have it register. Okay. All right. So more about IEEE. Numbers are stored in double precision. You have 8 bytes or 64 bits. There's also single precision that has half that storage, 32 bits. How are the 64 bits allocated? 1 bit is for the sign, 0 for positive and 1 for negative. 11 bits are reserved for the exponent, and then the remaining 52 bits are for mantissa. But because of normalization, we actually have 53 digits of precision because there's an implied 1 at the front of the mantissa. And then this is what I was getting into earlier, that most of the time we normalize, so there's no need to store that leading digit. Now here's the strange part. We have 11 bits set aside for the exponent. So that leads to 2,048 possible exponents. So you would think that this would be the exponent range. So minus 1023 up to positive 1024. But it's not. Earlier I told you what the exponents were, minus 1022 to 1023. So these extreme values are not allowed to be used as exponents. The reason why is IEEE has decreed that when exponents correspond to these values, that's for special cases like inf or NaN. So they're not included in the range of allowed exponents. So that's why these are the properties of IEEE double precision floating point. And then for single precision, same base, of course, it's all binary. 24 bits of precision, and then this is your range of exponents that's much smaller because only 4 bytes, yeah, the 4 bytes total, and 8 bits instead of 11 are set aside for the exponent. If you want to get some insight into how MATLAB stores and represents floating point numbers, you can use one of the formats that came up in the homework, format hex. And I told you before that this is my favorite format. Yeah, it's total garbage, to be uninitiated. Hex is convenient because one hex digit, hex is base 16, which is 2 to the 4th. So one hex digit corresponds to 4 binary digits. So the first binary digit is a sign bit. Like I said, 0 for positive, 1 for negative. Next 11 bit digits. Okay, so we have the exponent, but the exponent gives you a number from 0 to 2047. You have to subtract 1023 from that to get the actual exponent value. All the remaining bits are the mantissa. Okay, and I don't have a ton of time, but I do have some time to show format hex. Okay. Hold on. Oops. Okay. So, I'm back to MATLAB. If I do format hex. So any numbers I type at this point are going to occur in hex format. So I'm just going to make up a number here. I'll do a negative power of 2 for convenience. 1 over 64. Okay, and now we have this gobbledygook here. So what does this mean? 3 F9, and then all these zeros. I'm going to convert this to binary. So 3, if I 3 in binary would be 1 1. So the 3 corresponds to each one of these characters corresponds to 4 binary digits. So 3 would be 0 0 1 1. And then the F so remember, I mentioned this earlier, A through F, letters A through F correspond to the hex digits 10 through 15. So F is 15, that's 1 1 1 1 in binary. And then we have 9, which is 1 0 0 1 in binary. And then everything else is 0. Okay. Now, the first binary digit is a sign bit. And that's, in this case, because it's 0, that means the number is positive. The next 11 bits, so 0 1 1, 1 1 1 1, 1 0 0 1, that corresponds to the exponent. But what exponent is that? So I need to convert this number to decimal. Okay, so if I start counting from right to left, so I have this is my ones place, 2 4 plus 8, 8, and then 15 plus 32 plus 64 plus 28 plus 6 plus 12 plus 10.
8.
1 2 3 4 5 6 7. Okay. So all these numbers added together correspond to these powers of 2 that have a non-zero digit. So I have MATLAB added all together for me, and I get, oh, whoops, that didn't help me at all. Convert back to format short to actually see what this number is. 1017. Okay. This value, so to subtract 1023 to get exponent, E, which is equal to minus 6. which makes perfect sense because 1/64, the number I was representing in the first place, that's 2 to the minus 6. So it ought to have an exponent of 6. Now the mantissa, in this case, is all zeros. But there's an implied 1 due to normalization. And the 1 that's not stored. So the actual mantissa is equal to 1.000053 total digit. So this floating point number is 1, the mantissa, plus 1, the sign bit mantissa, times 2 to the minus 6, which is the exponent.
How many zeros did you?
It doesn't matter how I type it, but the mantissa is representing 53 total digits, so I wasn't going to type out all 53. But if you want to type out 53 zeros, you can. Okay. So questions about what we saw in text format. We go back to format hex. Now look at the smallest number that I can. Or for unit round off, 2 to the minus. Oh, actually, I don't want that. I want 2 to the minus 1074. Okay, so in this case, all the bits are 0. So we have the sign bit 0 for positive. Exponent is equal to minus 1023. And then the mantissa is equal to 2 to the minus. Okay, here's the strange part. The bits coming from the exponent point to minus 1023, but if the mantissa being 2 to the minus 52, that's the least significant possible digit. Actual exponent is minus 1022, because if I take this exponent, add them together, I get to minus 1074. So even though what's represented is minus 1023, this is a signal that what this tells the hardware, the computer hardware, is that denormalization is being used. Because if the exponent stored here was minus 1022, the number would be interpreted as being normalized, and the mantissa would be interpreted as not 2 to minus 52, but 1 plus 2 to minus 52, which would be a very different number. Now what we see here is that powers of 2 can be represented exactly in floating point number system. That means that other numbers that can be represented exactly in decimal cannot be represented exactly in binary. So for example, if I'm still in format hex, if I do like a 0.1 and I get all of that, so what does this mean? If I pick this one apart, I know class is almost over. The exponents, okay, so that's 0, 1, 1, B, which is 11 in hexadecimal, so that would be 8. Okay, so that gives you the exponent. And then the mantissa, I have all these 9s here, so that's 1, 0, 0, 1, 1, 0, 0, 1, and so on. If it is A at the end, that's 10 in hexadecimal, so that'd be 1, 0, 1, 0. That's it. last digit being even, it's rounding to even. So if I were to work out what this number is, I wouldn't have time to do that now. Represented number is not exactly 0.1. It is not possible to write 0.1 or 1/10 exactly using a finite number of fractions whose denominators are powers of 2. So even with a simple number like this, I mean, we expect that number in like irrational numbers like square root of 2 or pi could not be represented exactly because they have an infinite decimal expansion. But even numbers that have a finite terminating decimal expansion, like 1/10, cannot be represented exactly in a binary-based floating point number system. So if you really want to, you can work out what this is and see how close it gets. Okay. Nothing in this overlook because I didn't do everything in this. Apparently, when I did this 2 years ago, I spent a ton of time playing around with format hex. But the class really got tired of it. So you all don't get that, or maybe next time. Well, I have to continue with floating point issues next time. Okay, I'm going to stop here. We're for reals. Okay, but I'll stick around in case anyone has any questions about this.
Homework.
Yes, okay. For a bit anyway, all right, so. I'll read more.